Hey everyone, today we're looking at how it is that we display quantitative data. And we're going to specifically be looking at dot plots and stem plots. Dot plots you know and are super familiar with, and stem plots are something entirely new. So this really marks a big important step. We're moving away from everything we did with categorical data last week into quantitative variables. So we're moving into going away from looking at data that involved words or putting things into categories, and we're moving into data that involves numbers. Okay, so what are quantitative variables? Those are variables that deal with, you guessed it, numbers. You know this. So again, what's a dot plot? We've done this a bunch of times. We did it with hiring discrimination, where you guys did a simulation, you came up with a number, I gave you a beautiful little sticker, you put it on the line, and we looked at the distribution. So in order to just do, again, I'm going to do this briefly because we've dot plotted before. When we're looking at a dot plot, each data value is shown as a dot. It's nice, it's easy, it's got a lot of dots. So in order to do this, we need a data set. And I grabbed this particular data set because it's near and dear to many seniors' hearts. This is data straight from that Naviance that you love so much. It's data about the number of letters of recommendations that different teachers at H&A write. Okay, so this is all the number of the letters of rec that they wrote, and I took this data right before COVID. So I can look at this and be like, okay, the lowest of those that wrote letters was 1. It looks like the highest was 34. So, there's a range there. But I don't really get a full grasp of this from looking at this data. So I'm going to make a dot plot because that's going to give me a better representation of what's going on. So I'm going to draw an axis, and I'm going to set my upper and lower from 0 to really past 30 at 35. And then I would simply individually plot every single one of these points. Right? And that would take some time. We've done this before with stickers, right? So here are all of my individual dots that correspond to the data points. So when you see the dot plot in this way, we can take a look at this and be like, what is this distribution? And you might be like, oh, this is taking a long time. Why do we do this? Because this is really the first vital step in understanding your data, seeing where that distribution lies, trying to see this relationship. And when I look at this relationship and kind of draw a picture of this distribution, I can see right away that there's a large number here, and there are only a couple of teachers that have high numbers, that most of them fall into this 0 to maybe 7 range, but that there are 1, 2, 3, 4, 5, 6 different teachers who write more than that. And so although I might be able to see this on the data table here, looking at it in a dot plot is a way easier way to look at the data. Okay, so I mentioned that looking at the pictures of the representation of the data in a dot plot is important to understanding the relationship. So how is it that we examine the distribution of a quantitative variable? What are the key points to it? So the first key point is to look at the overall pattern and departures from the pattern. So I want to look at what I see and the outlier. So again, in this particular case, I have this, a lot of data around the 0 to 7 range, and some data that's kind of far away. So I'm seeing an overall pattern, and I'm looking out for the departures. Then I want to actually describe this. And I'm going to describe the distribution in terms of 3 things, which we're going to define in a second. One is called shape, one is called center, and one is called variability. And then I'm going to look at, are there any data points that are way outside of the realm of what I think might be the rest of the data? Like taking a look at here at this data point here, that is way higher than the rest of the data. In fact, all of these data points might be outliers. They might lie far outside of the realm of most of the data which we see over here. right? And we have a mathematical way to find outliers, and we'll talk about that later. But an outlier is basically, am I seeing something that is like out of the ordinary? So those are the main things that I'm looking for. And the way that we remember this is shape, center, variability, and outliers. And this tends to be the order that we put this in. I mean, I guess if Visco helps you remember this, you could say Visco. But, you know, or however you want to remember it. But shape, center, variability, and outlier is how we can remember this. Let's start with shape. If you look at this dot plot we would describe as roughly symmetrical. And this is very key that I use the word roughly, right? I don't want to say that it's perfectly symmetrical or imply that it's completely symmetrical, because no data really is. So I want to say roughly symmetrical. So a distribution is roughly symmetric if the right side of the graph, containing half of the observations with the largest values, is approximately a mirror image of the left side. So again, a distribution is roughly symmetric if the right side of the graph, containing the half of observations with the largest values, is approximately a mirror image of the left side. So I can describe the shape, and again, this is the first part of how we describe a distribution. I can describe the shape as symmetric. Sometimes it's not symmetric though. Sometimes a distribution is skewed, and we talked about, you might have even heard about skewed data, where I have data going to one side or another, like a large portion of the data is in one side and not the other. So a distribution is skewed to the right if the right side is much longer than the left side. And here's what I mean by longer. If I take the distribution and draw this pretty picture, this one just kind of trails off, and that side is a little bit longer. That picture isn't the best, but there you go. That this side is the longer side, and the longer side happens to be on the right-hand side, so we say it's skewed to the right. I often call this like a tail in the data. So when my tail is on the right side, we would say it's skewed right. A distribution is skewed to the left if the left side of the graph is much longer than the right. So here's my tail. This side is longer. This is my tail on this side. So again, the bottom picture here is skewed to the left. Now, when you're looking at data, I'm going to want to know, is this roughly symmetric? Is it skewed to the right? Is it skewed to the left? And the skewed data, it's going to be important to know because we handle different things based on whether or not they're skewed or symmetric. So this is really the first part of how we're going to describe this shape. The next part of describing the shape is talking about the peaks. So this particular data, looking at quiz scores, it has one peak. So we would say the distribution of a quantitative variable is unimodal if it has a single peak, meaning that it has one peak. So unimodal. Most of the data that we look at is unimodal, although occasionally we have data that is bimodal. The distribution of a quantitative variable is bimodal if it has two distinct clusters and peaks. And this might be true for how long it takes someone to do something. Maybe it takes you this amount of time or this amount of time, and rarely is there anything between. So that might be data that's bimodal. It's not really common for us to see bimodal data, but I wanted to tell you about it. Sometimes, though, we do see this, where a distribution is approximately symmetric. And yes, I know I just used the term roughly symmetric, and now I'm saying approximately symmetric. And what in the world is the difference? The difference here is I don't really have any peak, right? So can I describe that whole thing as roughly symmetric? And there appears, like, I might even say, like, there appears to be no clear mode or no clear peak. That's fine too. But the distribution of a quantitative variable is approximately symmetric if the frequencies are about the same for all the values. And I feel like approximately symmetric is written a lot when you're trying to do a problem, they'll be like, the data is approximately symmetric. What's the likelihood of getting a data point between this and this? And basically what they mean by that is, hey, look, my data kind of looks like a box where all the data is in there. Okay, so that's how we would describe shape. Now we're going to deal with center and outliers another day, but I just wanted to talk about shape today, one piece of how we describe it. And again, to do shape, I generally look at a dot plot, but there is another plot that we can look at and that we need to talk about today. And that graph that we need to talk about is the stem plot. So let's get into how to stem plot. A stem plot is a way to represent a small set of data. Sometimes they're called stem and leaf plots. Sometimes they're called stem plots. They are not the easiest plot in the world, so we're going to take a little bit of time to explain them. I'm going to write down these steps, and I know these steps don't make any sense right now without a data set. So I'm going to come up with a small data set, and then I'll go through each step, and then I'll explain the steps another time as well. So to come up with a smaller data set than this data set on the left that we've been working with already today about letters of rec, let's talk about number of cookies. Faculty ate at the faculty staff meeting the other day. So maybe a couple people had like 1 cookie, and then some people had 2 cookies. Some people had 4. Some people had 5 or 6. I had like 10. I'm not gonna lie. So 10, 11, 12, something like that. So let's say this is the number of cookies eaten, and I want to create a stem and leaf plot because it's just a small set of data. I don't really need a dot plot for this. So essentially what I'm going to do is I'm going to choose a stem, decide what the stem should be and how many digits. So I look at these and I need to turn everything into the same number of digits, kind of like we do for a random digits table. And looking at this, I can make everything into 2 digits. The leaves can only have 1 digit, so the stems need to have the other. Since all of these data sets can have 2 digits, my stem is going to have 1 digit and my leaf the other. So I'm going to say all of the numbers that could be the first digit are either 0 or 1. And then I make this little line here. So the first step I did was decided what the stem should be, like how many digits. And I made that up by looking at how many digits were in my data. I have to have the same number of digits, so 2. And then just being like, well, what was the first digit? Because I have to save 1 digit for the leaves. Now I'm going to write the leaf on the proper stem. And yes, it's called a leaf and a stem. So basically, I'm going to take each of these and write them. So my first one is 1. My second data point, 1. My third, 1. Then 2, then 2, then 4, then 5, then 6. So I can cross these off as I go. But those are all of the values that have a first digit of 0. And there are 2 values that have a first digit of 1, 10 and 12. So how in the world do you read a stem plot? This number right here that I'm underlining here, the 2, really means 12. 1 and 2 is 12. Right? So I've arranged the leaves in numerical order out from the stem, and I need to have a key. So I need to say somewhere that 1/2 or 0/1, doesn't really matter what I put as long as we understand this, means 12 cookies eaten. And I'll do this in a better color. 12 cookies eaten. Okay, so this is the basic idea for how we do a stem plot. Right? So let's try this with this crazy data set we have over here. what's very, very incredibly unfortunate is that this order here of the numbers of letters of rec is not in any sort of order that's going to help me. So the first thing I really need to do is reorder this in numerical from like lowest to highest so that I can actually make a proper stem and leaf plot. So I know this is painful, but I'm going to have to go here and be like 1. Here's another 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 1. Here's another. Here's another. And here's another. Then I'm going to have to repeat that for the 2s. Now this is going to be a bit of a process. So I actually want you to try this with the person sitting next to you. I want you to take a second with the person next to you and put this in numerical order. You have this up on the screen. I know it's super tiny to read, so it's also in your OneNote, but I want you to take a look, put this in numerical order with you and your neighbor friends, and then think about, okay, what is a good stem for this? So go ahead to pause the video, and when we come back, we'll look at the order and talk about the stem. Okay, so hopefully you've had a chance to put these in order. The great thing about me not being here is if I'm wrong, you can't correct me. So we'll just assume that I have this correct, and if I'm missing some, I'm sorry. So this is what I got in the numerical order, and each of these can be made to have 2 digits, a lot with a 0 in front. So I've really got, I'm thinking in this particular case, I've got a 0, a 1, a 2, and a 3 as my particular stems. So I've gone ahead and made the stems. Now I need to put all of these in numerical order. Again, I want you to try this with your neighbor friend. So I'm going to start by saying, okay, we need to put all the ones. So I'm going to count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then my 2s, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so take a second now that we've got our stems, and I'm going to have you pause the video, and I want you to finish out drawing your stem plot. So this is what my stem plot looked like. And I haven't made the key yet, so maybe I want to highlight this like number that represents 18 letters, again, because the 1 here and the 8 here. So I would say, okay, 1, 8 means 18 letters of recommendation written. Okay, so I need some key as well, just so that people understand what this means. Now, if I'm looking at this particular stem and leaf plot, goodness gracious, there are so many values that are here at the 0 that this might really be really confusing. So what I might want to do is add some sort of split stem. So yes, I made a 0 and a 1 and a 2 and a 3, but maybe I want to split it up as to 0 through 5, 6 through 9, right? Or 1 through 15, something like that. So let's talk about what a split stem would look like. My old stem plot in the corner there just so you could see it. So this might be how I split this stem now. Right? And again, the key would actually be the same, 0/8 equals number of letters written, something like that, ... You would have more details, but I'm just trying to save some time here. So I put all my 1s, 1, 2, 3, 4, 5, 6, 7, 8, 9. Pretend this is the right number. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. And then maybe on this next one, I could put the 5s up here. 5, 5, 6, 7. And then here would be 11. This would be my value at 18 and 19. I have a value at 21, 24, nothing there, and then a value at 34. So again, this would be a split stem, right? So whatever you need to do to pictorially represent the data, but you can see that each of the leaves is one digit. So if I'm trying to do numbers like 120, 1, 2, 2, 3, and 1, 2, 2, 4, then my stem might be 1, 2, 2, and then my leaf would be 3 and 4, well, no comma there, 3 and 4. Right? So my stem can be multiple digits, but my leaves can only be one digit. Now there's one more aspect to a stem I want to show you, and that's back-to-back stem plots. So I actually split up the data into male and female teachers here at the school as to who receives the most requests for letters of rec to see might there be a difference between the number of letters that women had to write versus the number of letters that men have to write. And so if we were to do a back-to-back stem plot, essentially what I want to do is make the same stem, but I want to spread the data out onto either side. So I think we decided that it was good to do 0, 1, 2, and 3 for our stems, and I'm not going to split my stems here. So maybe I'm going to start with my females again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I know this takes a long time. 1, 2, 3. 1, 2, 3. So I'm just going to speed this up with a little magic. Okay, so magic numbers just appear. Okay, so here are all of the female teachers, and I might even write female here so that everyone knows. So this looks like a normal dot plot like everything we've done before. But what I'm also going to do on this same thing is put the male teachers. So I'm going to do this the same way, just backwards. So 1, 2, 3. They had 3 teachers who wrote one letter. So I would go 1, 2, 3. And 1, 2, 3, a 2 and a 3. And then 3 who are 4. Okay, and then 1 who was 19. We know it's you, Merle, now. Okay, so here's kind of the breakdown about how we do this, right? So now you can see this is what a back-to-back looks like. You have male versus female. So there's a bunch of different ways to stem and leaf plot, and you're going to be able to look at some, and you want to think about what these what would be good stems and how you might look at the leaves. Another thing to think about is the stem and leaf plot can actually show you the distribution. So if I were to draw this by looking at my side, like tilting my head this way and saying, okay, this distribution, then I would say, so kind of turning it like this. If I will, okay, that was a really bad distribution, but turning it in my head like this, then I would say, oh, look, hey, this is a really highly skewed data set. This is really skewed to the right here. This tail goes off to the right if I turn my head on the side there and say, this is right skewed data. So I don't have to have a dot plot to sort of show my skew. I can look at a stem and leaf plot as well. Okay. You might have a little bit of time left. If you do, I want you to check in with your bias group project members, see what else you need to do. And then if you finish in your bias groups, you can go ahead and start on your sapling homework. Have a great day.